Good morning to all of you. My today presentation topic is infrared spectroscopy of organic chemistry. Electromagnetic spectrum. Introductions. All compound containing covalent bond, whether organic or inorganic, absorb in the infrared region of the electromagnetic spectrum. In contrast to a UV spectrum which contain only a few bands, an IR spectrum contain a number of peaks which provide a wealth of information about the structures of the compound. Therefore, IR is by far the most widely used spectroscopic technique for determining the functional group present in an organic compound. Units of IR radiations. The position of absorption in the IR region can be expressed either in terms of wavelength in micrometers or in terms of wave number, that is, number of waves per centimeter. Thus, where V is the frequency. In Hertz, however, most chemists prefer to use wave number rather than wavelength as units, since the energy of radiation is directly proportional to the wave number. E is equal to h mu is equal to hc upon lambda hc into mu bar. Thus, the higher the wave number, higher the energy. Parts of IR region. The IR region of the electromagnetic spectrum extends from 0.8 to 200 micrometer. For convenience, it has been divided into three parts. The region which extends from 0.8 to 2.5 micrometer is called the near infrared region. That which extends from 2.5 to 15 micrometer is called the ordinary infrared region, and that which extend from 15 to 200 micrometer is called the far infrared region. The near infrared region corresponding to energy in the range 11.44 to 55.75 kilocalorie mole inverse, while the far infrared region corresponds to increase in the range of 0.14 to 1.9 kilocalorie mole inverse. Since there are only a few absorptions of organic molecules in this region, they are seldom used for spectroscopic purpose. The radiation in the ordinary infrared region have energy in the range 1.9 to 11.44 kilocalorie mole inverse, which correspond to energy difference commonly encountered in the vibrational state of organic compound. Consequently, almost all the organic compound show a number of absorptions in this region, and hence this region is extremely useful to an organic chemist. Principle of IR spectroscopy. The absorptions in the infrared region occur due to excitation of molecule from lower to the higher vibrational level. Since each vibrational level is associated with a number of closely spaced rotational levels, IR spectra may be regarded as vibrational rotational spectra. We know that the atoms in a molecule are not rigidly held but keeps on vibrating to and fro about an average internuclear distance. Thus, each bond has a characteristic stretching and bending frequency. At room temperature, most of the molecule of a sample will be in the lowest vibrational level, mu is equal to 0. However, when ordinary infrared radiations 2.5 to 15 micrometer are passed through the sample, some of the molecules will absorb a quantum of infrared radiations of appropriate energy and thus get excited from the lowest to the next higher vibrational level. Mu is equal to 1. In this higher vibrational level, the native frequency of the bond remain to be the same, but its amplitude increase. Due to this increased amplitude, an oscillating dipole will be set up in the molecule. The interaction of this oscillating dipole moment with the electric vector of the infrared radiations leads to absorption of energy. When the excited molecule reverts to the original ground state, the absorbed energy is released as heat. Since the absorptions in the IR region, like in other region, is quantized, therefore only a selected frequency of the incident radiation will be absorbed. As a result, each molecule will show a fixed number of peaks in the IR region. It may be noted that all the bonds in a molecule are not capable of absorbing infrared energy even if the frequency of the incident radiation exactly match the native frequency of the bond. Only those bonds which are accompanied by a change in dipole moment will absorb in the infrared region. Such vibrational transitions which are accompanied by a change in the dipole moment of the molecules are called infrared active transitions and hence are responsible for absorptions on energy in the infrared region. Conversely, those vibrational transitions which are not accompanied by a change in dipole moment of the molecules are not directly absorbed and are said to be infrared inactive transitions. For example, vibrational transitions of C double bond O, NH, OH, NO2 bonds are accompanied by a change in dipole moment and hence absorbed strongly in the infrared region. On the other hand, carbon-carbon double bond of symmetric alkenes and carbon-carbon triple bond of symmetric alkynes are not accompanied by any change in the dipole moment and hence do not absorb in the infrared region. Molecular vibration, type of fundamental vibration. We have stated above that atoms in a molecules are not rigidly held. These may be compared to a system of balls of different size connected to springs of varying strengths. Here balls corresponding to atoms and springs to chemical bonds, just as we can compress and extend or bend a spring in a similar way, bonds can be stretched or bent. As a result, there are two types of fundamental vibration for molecules, stretching and bending. In stretching vibrations, the distance between the atoms increase or decrease, but the atoms remain in the same bond axis. On the other hand, in bending vibrations, the position of the atoms change with respect to the original bond axis. These two types of vibrations are shown. For an AX2 system such as NH2, CH2, NO2, etc. Stretching and the bending vibrations. We know that more energy is required to stretch than to bend a spring. In a similar way, we can safely say that stretching vibration require more energy than bending vibration. In other words, stretching absorptions of a band will appear at higher energy, that is higher wave number in the infrared spectrum than the bending vibrations of the same bond. Bending vibrations are also called deformation vibrations. Further, since the absorptions of energy in the IR regions is a quantized process, therefore these stretching and bending vibrations will occur at certain quantized frequency. In nutshell, absorptions of ordinary infrared radiations corresponding to energy change of the order 1.90 to 11.44 kilojoule mole inverse, and this amount of energy is sufficient to bring out change in the stretching and bending vibrational frequency of covalent bonds in most of the organic compounds. Type of stretching vibrations. These are of the following two types. Symmetric stretching. Stretching vibrations is said to be symmetric if all the bonds are simultaneously stretched or compressed. It is denoted by symmetrical For example, CH symmetric stretching vibration of CH2 group absorbs at 2853 cm inverse. Asymmetric or asymmetric stretching. A stretching vibration is said to be antisymmetric if one bond is being stretched while the other is being compressed. It is generally denoted by mu asymmetric. For example, the antisymmetric stretching vibration of a CH2 group absorbed at 2926 cm inverse. In general, antisymmetric vibrations requires higher energy than symmetric vibrations and hence appear at higher wave number or lower wavelength in an IR spectrum. Types of bending vibrations or deformation. These are of two types. First is in plane bending vibrations and second is out of plane bending vibration. In plane bending vibrations, in these vibrations the two atoms remain in the same plane of the molecules. These are of the following two types. In plane scissoring deformation, in this bending mode the two atoms moves towards each other like blades of a scissors. For example, in the plane scissoring bending vibration of a CH2 group absorb at about 1465 cm inverse. In plane locking deformation, in this bending mode, the two atoms move in the same direction, first to one side and then to the other side. For example, in plane rocking vibration of a CH2 group absorbed at around 277 cm inverse. Out of plane bending deformation. In this vibrational mode, the two atoms moves out of the plane of the molecules. These are of the following two types. Out of plane wagging deformation. In this bending modes, both the atoms simultaneously move above or below the plane of the molecules with respect to the central atom. The wagging deformation of a CH2 group absorbed at about 1250 cm inverse. Out of plane twisting deformation. In this type of bending vibrations, one atom moves above and the other below the plane of the molecules with respect to the central atom. For example, the out of the plane twisting vibrations of a CH2 group like wagging vibrations absorb around 1250 cm inverse. All the four types of bending vibrations are shown below: scissoring, rocking, wagging, twisting. Position of absorption band. From the equations of Hooke's law, it is evident that the frequency of absorption of a stretching vibrations depends upon the following two factors. First one is strength of the bond or the force constant of a bond. Second is masses of the atoms forming the bond or the reduced mass of the system. The third factor which affects the absorption frequency is the type of molecular vibrations. Let us now discuss these three types factors one by one. Strength of the bond. Stronger the bond, higher is the stretching vibrational frequency. We know that the strength of the bond increase in the order single bond is less than the double bond, then the third bond, triple bond. Therefore, triple bond stretching vibrations, that is carbon carbon triple bond, carbon nitrogen triple bond, etc., absorb at a higher frequency or wave number than double bond stretching vibrations, that is the carbon carbon double bond, carbon oxygen double bond, carbon nitrogen double bond, which in turn absorb at a higher frequency than the single bond stretching vibrations: carbon carbon single bond, carbon oxygen single bond, carbon nitrogen single bond. Second one is masses of the atoms. The lower the masses of the atoms forming the single bonds or lower the reduced mass of the system, higher is the stretching frequency. The effect is particularly marked when one of the atom forming the single bond is a very small proton, that is carbon hydrogen bond single bond, oxygen hydrogen single bond, nitrogen-hydrogen single bond, which generally absorb in the region 37002 to 2630 cm inverse. For example, OH bond absorb near 3570 cm inverse, and the oxygen and deuterium bonds absorb around 2630 cm inverse. Here the strength of the bonds are nearly the same, but the masses of the atoms deuterium is double than that of the other protium. It may be noted that in order to predict exact trends, it is essential to consider both the force constant and the masses of the atoms together. In some cases, if the predictions are made on the basis of masses of the atoms alone, we are liable to commit mistakes. For example, on the basis of the masses of the atoms alone, we would expect that the stretching frequency should decrease in the order carbon hydrogen is greater than carbon nitrogen hydrogen, then oxygen hydrogen, then fluorine hydrogens. But in actual practice, they increase. The reason being that for constant increase in the order, carbon hydrogen is less then nitrogen hydrogen, then oxygen hydrogen, then fluorine hydrogens. Thus, hydrogen fluorine single bond absorb around 4138 cm inverse, oxygen hydrogen around 3570 cm inverse, nitrogen hydrogen single bond around 330 cm inverse, and carbon hydrogen around 330 cm inverse. Types of molecular vibrations. The frequency of an higher absorption band depends upon the type of the molecular vibrations, whether stretching or bending. We have already discussed above that stretching vibrations of a group requires more energy and hence appear at a higher frequency or the wave number than the bending vibrations of the same group. Further, among stretching vibrations, asymmetric stretching vibrations absorb at a higher frequency than the corresponding symmetric stretching vibration. For example, asymmetric stretching of a CH2 group absorb at 2962 cm inverse, while symmetric stretching vibration absorb at 2853 cm inverse. Similarly, different bending vibrations of a CH2 group absorb at a different frequency or wave number. Scissoring at 1465 cm inverse, wagging and twisting around 1250 cm inverse, while rocking vibration absorb at about 270 cm inverse. Thank you.